What's your turn? Dum-de-dum. Hey, buggers. Beep. Beep. All right, looks like we're at 20, so I will begin. Good morning, everyone. This should be a fairly short and sweet lesson for today, so that's nice. The first thing I wanted to talk about is this isn't the official name of it, but I just call it this in my head, the sneaky form of Newton's second law. Okay, so that's the first thing we're going to talk about today. So Newton's second law is that the net force equals mass times acceleration. But what if we were to actually write the definition of acceleration? So acceleration is the rate of change of velocity. So change in velocity divided by change in time. So this is kind of an expanded form of Newton's second law, okay? And we can see right here that we have mass times velocity, but we have a delta in there as well. So this is actually the change in momentum divided by the change in time. So this is the sneaky form of Newton's second law. Net force is the rate of change of momentum. Okay? Okay? So, anyways, we can actually use this as a pretty useful equation. So let's do an example. Suppose we have a wall, and there's a ball. Let's say the ball has a mass of 0.2 kilograms. And the ball approaches the wall with a speed of, let's say, I don't know, 20 meters per second. And we'll say that the collision isn't perfectly elastic. So after hitting the wall, the ball bounces back and it loses some of its speed. So it bounces back with only 15 meters per second of speed. Now, you're watching this collision with an ultra high speed camera, okay? And so your ultra high speed camera is so good at observing fast things, that you can actually see how long the ball is in contact with the wall for. Okay, so high-speed camera shows that the time of contact with the wall is 0.005 seconds. Okay, so it's able to, it's taking thousands of frames per second, and it's able to see that the time of contact of the ball with the wall is that. We can use the sneaky form of Newton's second law to estimate the force the wall exerts on the ball. Okay, so here's what we do. We find the initial momentum. The initial momentum, recall the formula for momentum is mass times velocity. So the initial momentum is going to be 0.2 times 20. Okay, which is what? 4 kilogram meters per second. The final momentum is the final momentum is going to be, you have a mass of 0.2 kilograms, but it's going to the left at 15 meters per second. So I'm going to make sure to put the minus sign in there to indicate that it's going to the left. And so that is -3 kilogram meters per second. So from that, we can determine that the change in momentum, which would be P final minus P initial, is going to be -3 minus 4. So -7 kilogram meters per second. And then the change in momentum over the change in time, okay, is equal to -7 over 0.005, which is -1400 newtons, is the force of impact. Okay, the reason it's negative is because the wall pushes the ball to the left, right? That's why it bounces back to the left. So that's an example of using the sneaky form of Newton's second law to find the force of impact. Okay, so it's a pretty useful way to think about it when you need to calculate a force. Second part of today's lesson, we're going to define something called impulse. Okay, and impulse is defined, so we're going to learn 2 definitions of impulse. So the first definition is for a constant force. Okay, for a constant force, the impulse is denoted by J, and it is equal to the force that acts times the time that it acts for. Okay, so this is the definition of impulse for a constant force. So this makes it pretty easy to determine the units of impulse. All right. The units of impulse are going to be units of force times time. So newtons times seconds. Okay. Impulse is used a whole lot in rocketry because if you have a rocket, the rocket exerts a certain thrust for a certain amount of time. So basically a rocket will fire until its fuel runs out, so that the time is the time for the fuel to run out, and the force is the force of the thrust of the rocket. So why is it useful to define impulse? Okay. Why is it useful to define impulse? Well, we have to go to the sneaky form of Newton's second law. So what if we have the sneaky form of Newton's second law? Rate of change of momentum is equal to net force. And then what if I multiply both sides by delta t? Okay. So if I multiply both sides by delta t, I get change in momentum is equal to the net force times delta t. But hey, look, impulse is force times delta t. We have force times delta t. So what that means is that the change in momentum of an object is equal to the impulse, but not just any impulse, the impulse due to the net force. Okay? The impulse due to the net force. Okay, so we can define impulse for any one of the forces that are acting. Okay, but that might not be the net force. Okay, so we could talk about what is the impulse due to gravity. We could talk about what is the impulse due to friction, etc. But those aren't related to the momentum. It's only the impulse due to the net force acting on an object that is equal to the change in momentum. Okay, so impulse due to the net force is equal to change in momentum. Okay, so that's an important point. So let's do an example. So let's suppose we have a 3 kilogram object falls for 7 seconds. All right. A 3 kilogram object falls for 7 seconds. Calculate the impulse. Due to gravity. Well, the impulse is force times the time elapsed. The force that we are talking about is the gravitational force. So mg delta t. All right. So we have m, which is 3, gravity, which is 10, and the time elapsed, which is 7 seconds. So that would give us 210 Newton seconds of impulse. Okay? So that's a very simple example of calculating impulse. Let's do another example. a 3 kilogram object moves to the left at 11 meters per second. A net force of size 40 newtons to the right acts for 2 seconds. Okay, what is the final velocity? What is the final velocity of this 3 kilogram object? Okay, so because we have a net force acting, we are going to use this equation. Okay, change in momentum is J net. The initial momentum, it starts out moving to the left at 11 meters per second, so that's going to be 3 times negative 11. So the initial momentum is negative 33 kilogram meters per second. The final momentum is unknown because we don't know how fast it's going in the end. So I'll just leave it as 3v final because the mass is 3 and the final velocity is unknown. So that means, and then we could also calculate the impulse due to the net force, which is going to be net force times time. The net force acts to the right, so it's going to be plus 40 times the time that the force acts for, which is 2 seconds. So that is plus 80 Newton seconds is the impulse. So now I use the fact that the change in momentum is equal to the net impulse. So the change in momentum is P final minus P initial, so that's 3V final minus, and we got to be really careful here because we have a double negative. So the momentum, the initial momentum is negative, and change in momentum is P final minus P initial. So we have minus minus. All right. Oops, 30. So minus 33 equals 80. Okay, so minus minus is plus. So we have 3V final plus 33 equals 80. Subtract the 33 over. So we have 47 equals 3V final. Divide both sides by 3. We get that V final is 15.6 plus 15.6 meters per second. All right, so that's an example of using the impulse. So I would like to teach you one more way of calculating impulse. All right. And that is the impulse due to a non-constant force. So what if we have a non-constant force? If you have a non-constant force, okay, then I have to tell you how is the force not constant. So maybe I give you a graph of force versus time. Okay. So we have force in newtons and time in seconds. And maybe that graph looks something like this. Maybe the force builds up and then it drops to 0. Okay. In this case, the impulse is the area under the curve. Okay. So impulse is equal to the area under a force time graph. So that is a key factoid. All right. So let's go ahead and turn this into an example. So let's suppose, so I'm going to actually put numbers on here. Let's suppose that this force ramps up from 0 seconds to 5 seconds. And let's suppose that the peak force is 100 newtons. All right. And let's suppose that this force acts. What are you doing, Mr. Bugs? On a, let's say a 4 kilogram object initially at rest. Okay? What is the final velocity of this object after this force acts? Okay, so how are we going to do this? Well, we look at our initial momentum. Because it's initially at rest, the initial momentum is 0. Okay. The final momentum is going to be 4 times whatever the final velocity is. So that means that the change in momentum is going to be final minus initial. So it's just going to be 4v final. All right. The impulse, and by the way, we'll say this is the net force. So this would be the net impulse. So that's going to be the area under the curve. Okay. This is a triangular shape, so we have 1/2 times the base, which is 5, times the height, which is 100. So that's equal to 250 Newton seconds of impulse. So now we use, again, the same equation. Change in momentum is J net. So I have 250 equals 4V final. So that means that V final, after dividing by 4, we get 125 divided by 2, which is 62.5 meters per second is the velocity, the final velocity. Okay. So I do want to just make one comment. Okay. Your midterm 2 is coming up after Thanksgiving vacation, and midterm 2 is going to have both energy and momentum on it, and it's really easy to get them confused because energy has kinetic energy, which is 1/2 mv squared. And then it also has momentum, which is mv. So these two things are closely related, but they're not the same, and so it's easy to get confused. So I did want to talk just really briefly about work versus impulse. So you might recall that work is the area under the curve of a force position graph. That is work. Okay. If you have a force time graph, then the area under the curve is impulse. So they're both areas under the curve, but they're areas under the curve of different graphs. So you really, this is the part where you might remember when I was talking about motion graphs, I said most important part is to read the axes. Okay. This is one of the reasons why, because you can easily mix these up. Work is equal to the change in energy. So work is energy given to an object. Impulse is equal to the change in momentum. So impulse is momentum given to the object. Okay, so make sure you understand work versus impulse. Okay? So they're closely related, but they're not the same thing. Basically, momentum or impulse is to momentum what work is to energy. Okay? So anyways, that's my lesson for today. Short and sweet, and I will see you in the Zoom room.